Now we are back with the creation of a 4-bar linkage that is actuated by springs. Now, just to recap what we have here, let's try to find a suitable view for the system. And if I hit start, the system will collapse. We remember that these two bars, the arm down and arm up, have colliding properties. What we need to do is to apply a spring that is in between these two bars. Now, recalling how the particular kind of configuration of our lamp was, we remember that we need to have an insertion point that is at 50 millimeters from the upper joint, which I'm pointing right now. Therefore, we select a cord and we connect it in a generic place on the upper bar. In order to position it, we double click on it and we select position, in this case, not world position, but position, which is going to be with respect to the center of gravity of the bar. We can, now the bar was 10 millimeters in diameter, so we want to be on the radius, so we select 5 here, 0, and the length of the bar was 350, so divided by 2 is 175 millimeters. Therefore, we have to position it at 125 millimeters, actually in this case minus, from the center of gravity, and making sure that we have a proper orientation. So these numbers should be either 90 or 0 or 180. Close. The second point is much easier. We're going to position it to close to the center of gravity of the second bar. So if we do a little rotation here, there is actually one trick. If we hit property of the bar and appearance, we can actually show where the center of mass is. Now this does not change the size of the bar, it's just a point that indicates where the coordinate frame is. So close. So select the frame and position it on this second system. For some reason it did not work. Try again. So there is some problem with the program that I'm using. Here it is. So click on the cord, click on the second bar, double click on the cord, or eventually right click, look at the position, and we're going to choose again 5 millimeters to be on the radius, 0 to be on the axis, and in this case 0 to be at 0 length. And we can set up here 0, or let's see, okay, let's say this is 90 degrees now. Perfect. Close. So what I have to do right now is to connect these two reference frame with a spring. So one reference spring is selected, control and making sure to select the second reference frame, select the constraint, and in this case linear spring. Now I'll be asked, okay, between the chord on arm down and the chord on arm up. Don't move the chords and create. Now I have a spring and I need to set the properties of the spring. So by rotating a little bit and putting into a better view, clicking on the spring, we can find up here spring/damper, and what we had set up to begin with was 2 and a very low damping. So we can hit apply, close, and run the simulation. We'll see that we have a very ample oscillation, but the system is basically not damped. All the damping is just given by the spring, and you can see that it takes a long while for the system to stabilize in a condition, in an equilibrium condition. So we stop, go back, and click on the spring again, and this time we are going to impose a 0.02 Newton per second on millimeters of damping. We apply and close, and in this case we should see that the system dampens very quickly. The system actually does not oscillate, and therefore this is a overdamped system. So let's stop, go back, click, and let's set up, for example, 0.02, apply, close, and run the simulation again. And now we can see that the system still oscillates, but it will stabilize very quickly around a position of equilibrium. Stop. Now, what if we want to see this oscillation? For example, we want to see the position of this copy of the bass. Let's give it actually another name. Let's call it, okay, click, and effector, which is a common term for robotics, where you have one part that is connected to the ground, which is the bass, and the other one is the end effector, where the system interacts with the environment. So if you click on the white here on the screen and then hit X, you can look the system from the X axis. So if we go back to the initial condition, we can track, for example, the position of this particular piece. So we can click on it and we go on insert meter, and here is what we can track. We can track the position, the velocity, the acceleration, the linear momentum, the orientation of the system, angular velocity, angular acceleration, and if we have a finite element result, we could track that as well. In particular, now we just want to track the position of the system and see how the system oscillates. So we can simply run the simulation and we'll see X, Y, and Z here for the position of the system with respect to the center, or actually with respect to the world position. Stop. So I can rearrange these, for example, in this fashion. And rearrange the part of the graph in this fashion. Zooming a little bit. Now, you see here clearly the oscillation of the system that is dampened down, and then everything is stabilized. If we want to only take a look at the Z, we can double click, go on meter, and on axis, and then select which axis we want to see. In particular, we want to see the Z, and this fit the axis. At the same time, we have formulas, and here we can have the formula to describe that particular coordinate. So this is still body 16. Dot P means the position. Dot Z means that in the direction of Z. So if we uncheck the other, you see that up here the X and Y have disappeared, and the only thing that I'm showing is the X-axis. This is important when I want to export the file, export this particular graph to an Excel file. So close, and for now we can cut here on how to make a meter and how to add a spring.